All right, so let's go ahead back and let's hit the high points of this slide so we're all on the same page. Again, what is an octet? 8 valence electrons. Very good. Okay? So we've got a few things we need to pay attention to because tomorrow we're going to begin drawing Lewis structures, and I've got to make sure you understand how to draw them. It's going to be very critical. So I want to talk about the 3 exceptions. There are 2 elements that do not have to have 8. Who are those 2? Hydrogen and boron. Okay? Hydrogen and boron. Hydrogen only has to have how many? 2. Listen to the way I ask this. Can boron have 8? Yes. But what can it also have and still be stable? 6. Okay? Is it possible to have more than 8? What do we call that? Thank you, ma'am. They're expanded octets. Now, again, this is very important, and you remember who those elements are that can. There's the first word that's the most important word. What kind of elements? Non-metals. That's the first one. So if you're looking to your right on that big periodic table, what color or what side of that orange line? The right side. Then, which element and above do you start with? Phosphorus. So it's P, which is number 15, and up. And when I say up, I mean in value, not physically above, value above. So those are the things that we have. And again, I'm going to ask it. It's right there in front of you. Can noble gases have expanded octets? Yes, and you're going to see that in the very next slide. We talked about this, correct? All right, so the goal by the end of tomorrow is I could give you any one of these and you could draw. And I'm going to teach you step by step. In fact, I haven't showed you this yet, but, and again, I know it's a half sheet. I apologize. It's a little small, so you can't see it. But this is step by step exactly what you're going to do. It works every time. Okay, it works every single time. So you don't have to memorize steps. They're there in front of you, but guess what? You do it so many times, it becomes memorized. Okay? Yes, sir. Yeah. Okay? Do we do this one? Okay. Highlighting. Yep. All right, so this is where we start. So, please excuse my dear Aunt Sally. What does that tell you?
Parentheses, exponents, decimals, multiplication, decimal.
Divide. Okay, or PEMDAS, right? So that's math. The reason you know that is because you've been working with that since what grade? A long time, right? So chemistry has them too, but the reason you're not familiar with them is because you've never seen them. You've never heard them. We have one called VSEPR. Okay? VSEPR is an acronym for something, and it's an important one. What does VSEPR stand for is the important part. So here's what it stands for. VSEPR stands for valence shell. Now, there's 2 words that I want to talk about. One word you already know. What do we keep calling valence shell? They're the outermost. I want to add a new word to that. Yes, they're the outermost. But what else do they do? You're not going to know the answer, so we're going to write this down. They are the ones that do the bonding. So valence shell is the outermost electrons that bond. That bond. That's valence shell. All right, the next one. What is an electron pair? And yes, it's that simple. 2 electrons. Electron pair is just 2 electrons, right? Nothing more than that. Then, the other word we've got to talk about is this word. Repulsion. What does repulsion mean? To push apart. All right, my grammar people. Apart. 1 word, 2 words. 2 words. Okay.
No, 1 word.
Part? Part is 1.
Part.
That's not one person you listen to.
No, because I was thinking it's 1 word. Yep. Apart is 1 word. Okay? So, here's the important part. Not a part. VSEPR states, this is the definition. If you call Webster, say, hey Webster, what's your dictionary say? This is what he says. VSEPR states repulsion between valence electrons around an atom desired to be, highlight that next blue sentence, that next blue phrase, as far apart as possible. Why would electrons be far apart as possible? charges do what? Repel. Is that how you spell repel, or is there an A in there?
No, it's
Is that right? Okay. Like charges repel. What are the charges of both sets of electrons? Negative. Okay. So an example is the central beryllium is surrounded by only two bonded electron pairs. Just out of curiosity, do y'all have that bottom picture? All right, try to draw that below. Again, I apologize. Yep, actually go ahead and add the dots around the F's. It is important. Add the dots around the F's. Again, I sincerely apologize about how this printed, and I'll make a note of that. Okay. So again, according to Vesper, the bonded electrons will be as far apart from each other as possible. So the fluorines, let's look at the fluorines. And I'm going to come off of this page. Does anybody have that? Because I want to show you something. Very good. If not, I'll come back to this in just a second. When we draw, so this is beryllium, and I'm going to draw the modified version, just the simple version. Are those F's as far apart as they possibly can get? There's no way they can get any farther apart, right? So the point I'm trying to make is, could this be an option? Can they get farther apart in this situation? Yes. But in this one, are they as far apart as possible? Yes. So what I'm trying to get you to see is, if I drew a line from here to here, what degree angle is that? Very good. That's about the geometry that you have to know. Okay? So do that little blue and purple line on your drawing. Draw a little half moon or half circle connecting the F and the F and write 180 degrees. Okay? Now, here's the other concept that students struggle with in this, is you have to be able to spatially make yourself aware of how these atoms work. Because what dimension are molecules in? 3D. Can you draw 3D? I asked that yesterday, right? You can't draw 3D. Is it difficult to think three-dimensional? Yes. So when we're beginning to draw these, I'm going to go ahead and tell you, I'm going to draw some things today that you're going to say, that's not right. And I'm going to say, you're right. But you got to remember, I'm trying to draw it like it's three-dimensional. And I'll explain that once we get into that little part of the talking. Okay? All right. So there's two, I'm going to use one word for two different things. Have you heard the word diatomic before? Yes. Is hydrogen one of them? How many others are there? There are 6 of them, right? It's all the gens. Now, when I say gens, I know some of you you laugh at me, but it's hydrogen, nitrogen, oxygen, and the halogens, right? Okay, that's all the gens. Now, I'm also going to use diatomic in this connection. It's a silly way to think about it, but it should make sense. Is HCl a diatomic molecule? What does diatomic mean? 2 atoms. Is that 2 atoms? It is. Okay. It's just different from the definition that I've been using this entire time. The diatomics I've been using, we're talking about the ones that are the same. Do they have to be the same to technically be diatomic? No. Okay. So look at this. Is this a representation of those 2 molecules? So in terms of geometry, and again, when I say geometry, what am I talking about? The shape. Is there any other way to draw those? That's it, right? There's no other physical way to draw this. So if you had to assign a bond angle between those 2, what does it have to be? It's got to be 180 degrees. Does that make sense? So anytime there's 2 things, automatically, what's their bond angle? 180. All right. So let's read the next bullet down. So to predict the geometries, and again, I've said this over and over, but I want to make your fears go away. When you see that word, what am I asking for? Shape. When we're going to predict the shapes of more complicated molecules, one must consider the locations of these 2 things. Highlight those next green words. The shared and lone pairs surrounding the atoms. Now I want to add one word in here. What constitutes a shared pair? Starts with a B. A bond. The shared pair is the bond. One more time. The shared pair is the bond. How do you draw a lone pair? The dots. Very good. It's the dots. Very good. Matter of fact, you can actually make it more specific. I'm glad I heard somebody say one who said that. Thank you. How many dots? 2 dots. Thank you. Whoever said that, thank you. 2 dots. Okay? Now, again, so what we're fixing to look at is molecules with more than 2 atoms. Now, when you start reading this, I want you to know that I'm going to hand you a sheet of paper today that's going to take everything in this and water it down into one single sheet of paper. Okay? So it's going to look like it's a lot, but I'm going to give you one thing that gives you all this information. I'm going to take all the words out. Now, the first thing I need you to understand is kind of the language I'm going to be speaking in, because I need to use a reference point for everything we're going to talk about. So let's talk about the language first. When we start talking about any molecule, the central atom, and add this right here, the central molecule in the shape, okay? The central atom in the shape, we're gonna call that letter A. I know that kind of sounds crazy and that doesn't make sense yet, but I promise you that's all going to clear up at the end. We're going to call that letter A. Atoms that are bonded to the central atom, what letter are we going to call it? B. Okay? Now, I'm going ahead and forewarn you. Remember I just told you a second ago I'm going to give you a sheet of paper that's going to clear every bit of this up? Some people use X instead of B, but it means the exact same thing. The paper that I'm going to give you guys, I've looked for years for something that was perfect that I didn't have to recreate. That sheet of paper is perfect, other than the fact, instead of it using B, it uses X. Everything else is perfect. So just accept that sometimes you may see an X instead of a letter B. And again, I know that makes no sense, but I promise it will in just a few minutes. Okay, so when we have this molecule, so let me go back, I'm going to redraw this. Which element is the central atom? Is everybody okay with that? What letter stands for the central atom? A. What atoms are bonded to beryllium? F. Fluorine. Okay. What letter stands for the atoms bonded to the center? B. But here's the important question. How many B's are there? 2. Does that make logical sense? Okay, so let's come over here and let's look. The AB2, is that not exactly what I just drew? Is linear. How do I know that? Are these two things as far apart as possible? And what shape does that create? Do you agree that if you drew a line, that's a line? That's a line. And you've already told me, what degree angle is this? 180. That's all you have to do for that. That's pretty simple, right? Let's go to the next one. AB3. So now what have I done? I've added a bonded atom. Do you agree with that? Let me give you an example. I drew this yesterday for you. A, no, check, that's wrong. This is B. So draw that out to the side. So if you want to draw a little arrow, draw this to the middle bullet point. First of all, what element is the A, the center one? Try again. Does everyone agree that boron's the center element? Okay, so that's A. Are there any bonded atoms? So there are some B's. How many B's? Do you all agree this is a molecule for AB3? And Tony, you kind of look at me crazy. You with me? So do you agree that boron is the A? It's the center atom. Do you agree that B are the atoms bonded to the center? How many are there? There are 3. This is AB3. Does that make sense? Destiny, you with me? Destiny, you with me? You sure? Carolyn, you with me? You sure? I just want to make sure. Okay? All right. So, here's the next part you have to connect. Anytime the molecule is that shape, what is the name of that shape? trigonal planar. That's the part you have to memorize. Okay? Trigonal planar. Here's the simple, maybe possible, easy way to remember this. What's the shape of that? Triangle. You see it now? Okay, it's a triangle. Now, I'm going to draw another shape. Because what is the other thing attached to that shape?
128.
Now, so you're saying, how am I supposed to know that's 120? You're right. Time, experience, and memorization are going to help. But let me show you. If this were a pizza, how many of you like pizza? And I were to cut that pizza into 3 equal slices. First of all, how many degrees are in a circle? 360. So if I cut this pizza in perfect slices, how many degrees is this slice, and that slice, and that slice? 120 degrees. Does that make sense? So that's how this works. Now, I have a question. This is a difficult concept, but you've got to remember. Molecules are in what dimension? 3 dimension. Is this thing in my hand that shape? No. How can I turn it into it? We got to take one out, right? Now this is why it's still a little complicated. But I hold it this one down the road. Is that flat? Is that flat? Is that flat? Is that flat? So, I actually, because if you think about it, are these atoms, the red ones, as far apart as they possibly can get? They're not. The reason why is because I would have to flatten. Right, so if I could press this hard enough and make the black one touch my palm, would it then be far apart as possible? So, that's what these atoms are trying to do. And again, someone tell me why these red spheres are trying to push apart? Because what's running around each red atom? And what are electrons going to do to each other? Does that make sense? So, that is this shape. So do you agree that A is the black one is the center? That's A. Do you agree that there are 3 red things bonded to the center? So is that AB3? Okay. Again, what is the name? What is the name of that shape? Trigonal planar. Plane means flat. Okay. What's the degree angle again? 120. Yes, ma'am.
So if this triangle was planar,
Yep.
will it always be 120 degrees?
If it's this shape, yes. Okay. All right. Now, well, let's say somebody crazy comes along, somebody like Colin, and adds another one. So we've got AB4. So how do you get AB4? You add another bonded atom, right? Now, I'm going to come back to those other things, but do not draw this. And I'm going to tell you why in just a second. You remember how I led with, I'm going to draw some things that don't make sense. Remember how I said that? This is a situation. What was that?
It was an F1.
It's my harmonica.
Not by my iPhone.
Don't draw this. And I'm going to tell you why. My first question, though, this is a relevant question. Who is the center atom, the A? Carbon. Who are the B's? Hydrogens. How many B's? So is this AB4?
Yes.
I'm going to ask you a trick question, but I want you to answer it the right way. According to how this currently looks, are all of those H's as far apart as I can possibly get? Yes. You agree with that? If this were the right answer, what is the degree angle between all of these things?
90.
90. H to H is 90. Someone tell me why that's wrong. Very good. That is 2-dimensional.
Oh, yeah.
Exactly. So this is why this gets a little kind of strange until you see it enough. Molecules are in what dimension? 3D. So if I had more space, more room, could I spread them out farther? Is that this?
Yes.
Yes. How do you know it's that? It's got 4 bonded atoms. Are those things, so look right here, I'm going to back up so everybody can see what's happening. So from here to here, is that 90 degrees?
No.
You've learned that in geometry. That's the extent of a geometry you need, right?
Yeah.
So this is the geometry question. What do you call the angles less than 90? So A letter. Very good. What do you call them larger than 90? Is this an obtuse angle?
Yes.
Therefore, these numbers can't be 90. They must be what than 90? Greater than. Let's talk about exactly how much. Remember again, I'm going to remind you the third time I've said it today. I'm going to draw some things that look weird, but you have to remember one thing. Say what this is. So this is what I want you to draw. No, I want you to draw this. This is the one I want you to draw. Somewhere around the slide we're on. This is the tetrahedral. Okay. So if I ask you this question, based on the perspective that you are currently looking at, are those H's as far apart as possible?
No.
They're not. But they're in what dimension? That's in 2, but reality they're in the 3 dimension. So what I've done is I've essentially drawn it like this. So the H, this going straight down, is technically doing what? Coming out at you. And the 2 that are kind of down to the side are doing what? Going back into the void. Do you kind of see how the spatial awareness is key in this? It doesn't look right, but when you kind of say, okay, I can see the H coming out at me, and the 2 that are at an angle kind of kick back into the board, it kind of makes more sense. That's the hardest part of this unit, is picturing that 3-dimensionally. And when you can do that, everything gets easy. Okay? But if you can't, we can fight through that, we can battle through that. So again, I've already asked you, what is the model for this? A, B, what? You have to now attach 2 things. What is the name of this shape? Tetrahedral. What does tetra mean? Does anybody know what tetra? Tetra means 4. Well, that's easy because AB 4, right? Now, last question. Just a second ago, you told me that all those were 90. But then we discovered that these are more than 90. Specifically, using your PowerPoint, what is that angle? 109.5. That's the number you have to know. Yes, sir.
So, could you just like, every single, if you divide, wait, no, never mind.
You can't because it's 3-dimensional. And that's the hard part. Now, I'm forewarning you. There's going to be one like this on your test. You have to draw this tetrahedral. If you draw it like a cross or like a plus sign, it will be wrong. You have to draw it with angles. Yes, ma'am. Yes. Okay. All right. Now, so far, everything we've done has been an atom bonded to an atom, correct? But the previous slide said I must consider shared, and what do we say a shared pair is? A bond, and what else? Lone pair. So you also have this picture, right? So let's stay in the first column. Did we do that?
Yeah.
So it's a very simple question. In the black box, what is the AB model for that? AB2. Does everybody recognize that? Okay? Everybody okay with that? Let's go down. Have you seen trigonal planar yet? Are all of those little spheres 120 degrees apart? Yes. What is the AB model for this thing? Does that make total sense, right? Now let's look at the bottom. Now do you see how there's 3 dimensions to that picture? So it makes it a little easier to understand. What is the AB model to that? All right. Well, now we've got to make some adjustments. So again, all of those are those atoms bonded to the central atom. Just using your eyeballs, how can you tell they're bonded? It's a stick, right? Or a line. Is everybody with me on that? All right, now let's go to the middle column. What happened to get from there to there? You take what away?
A bond.
A bonded atom. And what did those 2 dots represent?
A lone pair.
Write that down. Those 2 dots represent a lone pair. All right. I'm going to make something very, very, very important. Actually, let me do this first. So, let's do the AB model. It's A, B, how many bonded atoms are there? 2. what else now do I now have? I've got a lone pair. There's another letter. Can anybody guess what that letter is?
C.
E.
Just E. Why?
It's an extra pair of electrons. Okay? It's an extra pair of electrons. Now, how many E's are there? How many extra pairs are there? Just one extra pair. Now, this is the next most important part. Look at the bond angles to the left one, the trigonal planar, the AB3. What were the bond angles between the atoms? 120. Now move to the middle. What is now the new bond angle? So what does that mean? Someone tell me something. So we took an atom and we swapped it for a lone pair, and did the bond angle get more or less? Got less. What happened? Someone kind of give me an analyzation of what caused that. Why did they get closer?
Because they ain't no bond. The bond made it less stable, whatever.
Not the bond,
The
the lone pair
in the long pair
made it less stable, which means it takes up more,
energy.
say the S word,
Space.
space. So here's how I want you to picture it. So right now, pretend my head is a bonded atom. It's weird, right? I'm at 120 degrees from my head to my arms. If you pulled my head off and swapped it with a lone pair of electrons, what would have to happen to my arms? They go down. Because lone pairs take up more space. That's what you need to know. Lone pairs take up, right under this slide, lone pairs take up more space. 6 words. Lone pairs take up more space. And I'm going to prove it to you 2 more times. I'm going to prove it to you 2 more times. Now, so looking at the bottom row, far left. How did we get from the bottom far left to the bottom middle? What had to happen, or what occurred? I took an atom off and swapped it with a lone pair. It's a mini quiz, real quick. Write it down, then I'll give you the answer. Write down the AB model for the bottom middle. Bottom middle. Write down the AB model for that. You should know how to do this now. A, how many B's? 3.
Yay.
Why 3?
Because
There's only 3 bonded atoms. Is there an E?
Yes.
Yes. How many? 1. Deal. Now again, it's an extra pair, not total electrons. It's an extra pair. Yes, ma'am.
So would it be A, B, E, 1?
Okay, so good question. Do you have to include the 1 here? No, but if you did, it's not wrong. Okay? It's one of those situations where you can or don't have to include 1. Me personally, I don't, but if you want to make it make sense, perfectly fine. Okay? Now, notice what happened. What is the bond angle on the bottom left one? 109.5. You swapped an atom for a lone pair. Do lone pairs take up more space or less space? You just wrote it. More. So since it takes up more space, did the angles get less? Yes. Did that happen? Everybody okay so far? Now let's, first of all, what is the name of that shape? Trigonal pyramidal. So does that kind of like a pyramid, the bottom 3? That's an easy way to remember. It looks like a pyramid. Okay? Now, how did you go from the bottom middle to the bottom right? What had to occur? We took another atom off and swapped it with a what? Lone pair. Write the AB model for that. So it's AB, how many? AB2. Is there an E?
Yes.
How many to E2? AB2, E2. Does that make sense? All right? Now, did the bond angle continue to go down? Yes. Why? The lone pair takes up more space. Now, what is the name of that molecule? Bent. So I'm going to circle something for you and tell you one of the challenges I have with some of this stuff. Are those 2 the same? They're different, but they're the same name. So here's why this has occurred. And I actually did some research. When I used to teach this many years ago, That top center one used to be called angular. And for some reason, the people in the science community decided to make it complicated on themselves and changed it to bent. The reason I teach it as bent is because AP Chemistry says that is bent. So if that question ever shows up on the AP exam, I don't want you to miss it because I taught it wrong. So I have to follow their rules. So unfortunately, these two things occur. Let me give you the good news. I'm never going to ask for that one on the test. But you may see it on a practice problem or something like that. So continue to follow the rules. But because of that situation, I'm not going to ask you to do the middle. Okay? But I at least wanted to show you. All right. Everything we just said, I've talked about. So I'm just putting words to it now. You guys do not have this, right? Let me redraw it for you to make it a little bit more sense. But I'm actually going to get you to do it two different ways. Actually, let me do it this way. Don't draw this yet. All right. Here's the problem. I've drawn this two-dimensional. What would you say the bond angles between those two things are? 90. Can I get them farther apart in three-dimensional?
Yes.
Yes. This is what I want you to draw. If someone had not been in this class and walked in and I said, which molecule have the H's farther apart, which one do you think they would say, the left one or the right? They would say left. But you know the one on the right is farther apart because it's in which dimension? The three-dimension. So your mind has to picture what? The one pointing straight down is doing what from the board? Coming out towards the board at you. And the two that are at the angles are doing what? Kick back in away from you. So how can I take this little guy and turn it into that? Take the top off. And that's it. Now, you can't see the dots, right? But the dots are there. So is one coming out at you?
Yes.
And two are kicked back away from you. That's the 3 dimension. Yes, ma'am. When they get there. Okay? All right. So also do me a favor. Write this. Does anyone remember the bond angle I just gave it to you? 107. The reason why this is 107 is because these guys take up more space. Okay? All right.
These two take up more space.
The lone pair take up more space. So that's why those H's are pushed a little closer together. So again, everything we've talked about, we've covered. So VSEPR can also account for the geometries. Again, as soon as you see the word geometry, what I'm asking for? Shape. The shape of molecules with unshared electron pairs. What do we call these unshared pairs? Lone pairs. Okay? So ammonia, which is NH3, which is that thing you guys just drew. The Lewis structure of ammonia shows the central nitrogen atom has one unshared pair. So what is the AB model for this thing? A, B, how many? 3. Is there an E? How many? 1. So AB3E. That's it. Yes, ma'am. Good. Okay. Now, here's again something that's important. VSEPR hypothesizes. What's the definition of a hypothesis? An educated yes. Now I know what you might think. Yes. Why are they guessing at this? Shouldn't they know what it is? And you're right. But here's the problem. We are constantly fine-tuning these models. In fact, here's a specific example of them fine-tuning. When I first started teaching this years ago, go back to the previous slide, the bottom right one where it said bent. It said, what is it bond angle say? 104.5. 104.5. It used to be 105. They've refined it. The technology has improved, and then they've actually taken it down half a degree. I was thinking, what's a half degree? So we're talking about atoms. Is that a big difference in atoms? Yes. So these numbers are slightly shifting occasionally. And so it's not locked in stone, and so that's why it's a hypothesis. So one more time, and what I'm fixing to tell you, you've already written down, but I want you to highlight it again. VSEPR hypothesizes lone pair occupy space around the nitrogen, just as bonding pairs do. However, this is what I want you to highlight. They actually take up what kind of space? More space than a bonded pair. So what's the result? And I want you to add these few words. So, bond angles are smaller. I want you to add those 4 words. So, bond angles are smaller. So again, everything that's on this slide I've already discussed. You've already seen it. Bond angles are smaller. All right, now, here's another picture to help some of this make sense. Take that back. Again, we've already talked about this. Taking into account one unshared pair, NH3 takes on what shape? Trigonal, pyramidal. That's AB3E, and it has a bond angle of 107. Okay? The shape of the molecule refers to the position of the atoms only. The geometry of ammonia is a pyramid with a triangular base with 2 lone pairs at the top. Is that not exactly what I drew in the blue? That's exactly what it is. Okay? Now the bottom, we'll put a big star beside this one. Okay? This is a silly question, but I'm going to ask it anyways. In water, H2O, which one would be the central molecule? Oxygen. Okay? But it has 2 unshared pairs. AB2E2, right? And its molecular geometry takes the shape of bent, which is what angle? 104.5. So I would highlight the 3 blue highlighted words. AB2E2 is bent with a bond angle of 104.5. Now, I'm fixing to draw something. And I'm going to go ahead and tell you it is wrong. And this is where students mess up every year. Because I know what you're going to say, and I get in arguments every year. My first question, is this A, B, 2, E, 2? Does everybody agree with that?
Yes.
Yes. Second of all, is this molecule symmetrical?
Yes.
Yeah, it is, right? The H's are perfect. The things are split, right? So does this look like the right shape for this molecule?
No. Wait.
Does it look like it?
Yes.
Here's the problem. It's not. You just told me the name of this molecule is what? Is that bent? It's not bent. So here's what happens. How can I turn this thing into that thing? To take 2 of them out.
Doesn't matter which one.
Doesn't matter. What is that shape? It's bent. So how do we take this and convert it into the proper shape? You push them down. So let me show you how. This is how I want you to draw. So again, I'm telling you on the test, there's going to be one of these. And if you draw it like the one on the left, it is wrong. The name of this molecule is bent. Is the one on the left bent? So you can't draw it that way. You have to draw it like the one on the right. The one on the right also. It does like an alien ship, right?
What does?
The one on the right. So those of you that are spatially aware, this is how I want you to picture the one on the left. So imagine the one on the left like this. Now this is flat, right? This is linear. It's like this. If you're looking from afar, can you tell that my arms are back?
No, not really.
You can, but 3-dimensionally can.
Yes.
Yes. So now can you tell? So when you turn that thing to the side, or look at it from the top, are they at an angle? That's how it works. So you have to think about it from a bent perspective. Okay. All right. Let's go with this. The unshared electron pairs repel each other more strongly than bonding. Put a big star beside that. You already know this, but I'm saying it again. The unshared, who do we call unshared? Very good. Change the color. These are lone pair. They repel how? More strongly. So that means the angles are smaller. All right, the last part of this picture I want to point out is this. This has one lone pair. Does everyone agree? Because what is that and that and that? Those are bonds, right? So what is the AB model for this one? AB3E. Everybody okay with that? All right. What is the bond angle of this? 107. Now let's come over here. This has a lone pair here and here. What's the bond angle? Now, this is, remember what I said a second ago? This is an old picture. You go ahead and go, Caroline. So cross that out, that's 104.5. So it's AB2E2. That's the difference there. Okay? I would. So one more time, very last bottom bullet. This is why the bond angles in ammonia and water are somewhat less than the 109.5 bond angles of a perfectly tetrahedral. And again, the reason why is because what do lone pair do in terms of space? Take up more space. Very good. All right. Last part. Crap, forgot about those two. VSEPR can be used to determine the, again, so as you see geometry, what is it? Shape. Okay. I'm going to show you these tomorrow. Determine the shape of many additional types of molecules. We've covered AB2E. We've covered AB2E2. There is an AB5. There's an AB6. And there are more. We'll talk about those tomorrow. Okay? Now, go ahead.
I was part of my question earlier. I was like, okay, if you have 8, did you go up to 8 or no?
You go up to 12.
Okay, well, yeah, I was like, so would you just still be,
Yep, same things.
same thing?
Now, okay, this is the largest. It does not get bigger. Gabriel, that is as big as it gets. There's nothing bigger than, and here's why. What is 6 times 2?
12.
There's your 12. Okay, that's as big as it gets. Okay, now put a big star beside this one. This is going to come into play in just a minute. Okay, treat double and triple bonds the same way as single bonds. So it's the same amount of space. So the point being is, do double bonds or triple bonds take up different space than a single bond? No, we treat them the exact same. Guys, I forgot something. I just want you to go back and write it down. It'll make more sense in just a second. Go back to, wow, maybe I didn't.
You did? Okay, that one was a legit.
Where did I write it earlier? Go back to this slide. Above this slide, I want you to write this one right here. All right. Find this slide. Above this slide, what's above the number 2? No.
Domains.
Domain. This is what I want you to write above this slide, is that. The reason why is in just a minute I'm going to help you do something. And you have to know what the word domain means. And if you don't know the definition of domain, you can't do what I'm going to ask you to do. So this is what a domain means. It's going to make things a whole lot easier, a whole lot faster. A domain is an attachment point to which atom? Central. There are only 2 things that can be attached to the central atom. What are those 2 things? Another atom. Now, I want to ask this just to make sure everyone's clear of how I wrote it. Does everyone understand why I put the S in parentheses?
Because it can be one
It can be one or multiple. right? So it doesn't have to be more, it doesn't have to be more, but it can be. So when you put an S in parentheses, that means it's possible to be more than one. So to make sure everybody understands what that means. So again, a domain is the attachment area to the central atom, and it can only be two things. It can be another atom, or it can be a lone pair or pairs of. Okay? Knew there was something I forgot. Last two slides. Okay?
Wait, you said last what?
Last two slides.
Wait, what was the number one? The other atom.
Yes, ma'am. Yes. Real quick. Now, this is something else that's very important. When we begin drawing these things tomorrow, we treat polyatomics similar to molecules. Peanut butter goes to jelly, this molecule goes to covalent. Except, when we draw them, what do we put them inside of? Brackets. And what do we put on the outside? The charge. Now, you guys do not have to flip with me, but I want to go back and prove this to you twice. Right here, look in the bottom center. What is that bottom center molecule drawn inside of? Brackets. And what's on the outside? Charge. Let me go back a few more slides and show you this again. And again, this is already on there. You've seen this once. Right there. All of those molecules are drawn inside of what? What's on the outside? Again, on the test, you've got to draw one of these. If you draw the molecule perfect, great, but you're going to lose points because ions have to be in brackets with charge. Last slide. Highlight the top part in blue. I know you can't see it on the board, but what's in blue? It says resonance structure. Resonance structure. If you call Webster, I need you to know what resonance means.
You done said that a lot.
I know, because there's definitions you have to know. Resonance means when one molecule, the same molecule, has two different shapes. Now, there's a key to that. One molecule has two different shapes. When drawing resonance structures, you can't change where the atoms are. You can only move the what around, highlighted in yellow. Now, this next bullet's the most important. What types of bonds are only allowed to give you resonance?
Double and triple.
If it does not have a double bond or a triple bond, can it have resonance? Not at all. So let me give you two examples. So look in this red box that I just drew. First of all, the first question is, what is the formula for both of those? Not that, the actual chemical formula. That make sense? Do you agree that both of these are O3? Are they different shapes? This one has double bond on the left. This one has double bond on the right. So is that a different shape? Yes, that means the double bond got moved. This is called resonance. Now, look at this funky. Look at, the first question I want to ask is what is the formula for every single one of those? SO3. Every single one of those have different shapes. Now, I don't want to spend a lot of time because I'm running out of it, but that molecule has 7 different possible shapes. Okay? When I have time tomorrow, I may come back and point something out about that because it's kind of unique and weird. All right, so here's what I'm going to do. I have probably the best news of the day. This is the last POGIL of the year. And I'm going to do half of it with you.
Let's get it.
Okay?
Is it a grade?
It is a grade. So we've got 15 minutes. I'm going to try to do half of it with you.
Yes.
And then we have
Easy.
Whatever
You
you
still have the ones from Unit 3. I mean the other ones.
This is the last one I'm going to give you.